In this video, we'll be doing the Hungarian method, also known as the Hungarian algorithm. Just as a quick recap, we will be quickly going over the important terms and concepts when it comes to using the Hungarian algorithm. What again is the assignment problem? The assignment problem is all about optimizing resource allocation. This can be in the form of minimizing resources like cost or maximizing performance metrics such as efficiency and profit. This is a special type of transportation problem where it is mathematically one-to-one functional, in a sense that one variable corresponds to one variable. For example, one employee can only be assigned to one task. Conversely, one task can only be assigned to one employee. The purpose of the assignment problem is to define the optimal one-to-one pairing for either minimum cost or maximum efficiency in productivity or output, etc. Going back to the problem, in a corporate office, a manager must assign 4 teammates to 4 different tasks. Each employee requires a different amount of time to complete each task. Determine the optimal assignment of employees to tasks that will minimize the total completion time. To make this example easier to understand, we can contextualize. So let's say we have 4 employees, Ellie, Catherine, Joseph, and Bruce, and we have the 4 tasks to plan, organize, lead, and control. Note that we are using the same numbers. We're just replacing the names and the tasks so that it's easier for you to understand. When it comes to using the Hungarian method, it gets simple when we visualize it like this. You can see that the main steps are here. So first, we have row reduction, column reduction, minimal zero lines, and a condition, which if the condition isn't met, there's a loop until finally it is met, and we get the final matrix here. So going back to our original matrix over here, what I'm gonna do to help visualize is just copy it here. So this is the same matrix as this one, and let's go back to the steps. So we know that the first step is row reduction. Essentially, what we'll be doing in this first part is going through each row and finding the smallest value. So let's do that now. So when we do row reduction over here, we get the smallest numbers, 5, 7, 8, and 6. What you want to do is subtract these numbers to their respective rows. For example, in this row, we're going to replace each value with the new value if you subtract 5. 10 minus 5, 5. 5 minus 5 is 0. 14 minus 5, you have 9. And 9 minus 5 is 4. So now we're going to do the same for the other rows. So subtract 7 from 8, 7, 17, and 8, and put the results over here. Do the same for 8, subtract here, and add the difference over here. So now this is our new matrix. And the second step is column reduction. So it's the same thing, but instead of going per row, we're gonna go down per column. So let's go through each column together. Here, we're gonna have the lowest number 1. Okay, don't mind the 1 here, it's very ugly. So here we have 1, 0, 4, 1. And you just do the same. But this time, of course, you subtract this lowest value to each value in its respective column. So let's do this together. 5 minus 1, we have 4. 1 minus 1, 0. And we have 4 again. And we have 5. And we'll just keep doing that for each column. So now we have this matrix over here. And now let's go to the third step, which is the minimal zero lines. Okay, so what this means is you want to cover all these zeros using lines. And you want to do the minimal number. So what you're gonna do is, so you see that this row, this column has an entire line of zeros. Again, we want to cover all the zeros using as least number of, with the least number of lines that we can. So we can cross out 4 zeros with this one line. And now we have a 0 left here and 2 zeros left here. Note that you can only draw horizontal and vertical lines. You can't do diagonal lines. So make sure to cover these ones with a horizontal line and cover this one with another line over here. So notice that all the zeros have been covered. So now count how many lines you have, and let's name that L. So notice that you have 3 lines. So L is 3. So 1, 2, 2, and 3. So let's go back over here. What is n? N here is the variable for our matrix dimension. In other words, how many employees do we have and how many tasks do we have? Remember, with assignment problems, this would be a square matrix. In other words, it's going to be the same number of employees and the same number of tasks. The dimension of our original matrix is 4 by 4. So we know that L is 3 because we have 3 lines. L is 3, you have 3 lines over here, and our dimension is 4. So notice that it's not equal because we have 3 and we have 4. So now we have to keep reducing the values uncovered until we eventually get the equal number. So let's see how this works. So when we say reduce the values uncovered, we mean these values outside of the crossed lines. So we have 4, 4, 5, 3, and 3, 2. These other numbers are crossed out. So when we're doing this part of the Hungarian algorithm, you want to get the minimum value here, which in this case is 2. You can probably guess what we're going to do next. We will subtract 2 from all these remaining uncovered numbers. So here, we know that 4 minus 2, we have 2 over here. And then we have 0. And then we have 4 minus 2 is 2 again. And then 5, we just keep 5 over here since it's crossed out. Another note is we have these intersection points. So we have here 0 and another 0. So we have these intersections over here. The rule is you subtract this lowest number, 2, to the other uncovered values. So you'll have another 0 over here. And then for these intersections, you just add it back. This ensures that the algorithm is mathematically sound because you're reducing these values, so you have to add these back. So what happens is 4 minus 2 becomes 2. So you keep these numbers that have been crossed out except for the ones that are intersections, because these ones you have to add 2 back in. Notice how 0 we add 2, 0 we add 2. And then we keep 0 here, 0, 6, 0, 0, 6, 0, 5, 0, 2, 5, 0, 2. And then we subtract 2 from these uncovered values. So 5 minus 2 is 3, 3 minus 2 is 1, 4 minus 2 is 2, 3 minus 2 is 1, and then 2 minus 2 is 0. So you have this matrix over here. So here we said that after reducing, let's go back over here. Let's see if the condition fits now. So we are going to do the minimal 0 lines. So let's go back to our matrix over here. So you can see that we can have 4 lines. It doesn't really matter which one you choose, you're gonna have 4 lines. So you can do it like this way. So you can do 1, 2, 3, and 4, or you can even do it 1, 2, 3, 4, or another pattern like 1, 2, 3, and 4. But you're gonna have L is 4. So now we know that this condition is satisfied. We have 4 lines with 4 as the dimension. So now we go to the last step, which is processing. We're going to do process of elimination. So this, I just copied it here so that it's cleaner. So this was our original matrix over here with Ellie, Catherine, Joseph, and Bruce, and the 4 tasks. So we have here this latest matrix that we made, and I just copied the tasks and employees. So now this is how we interpret the matrix. Let's start with these zeros. So we have a 0 here, 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 and here. So the way we interpret this is Ellie can only work on organizing. So these zeros represent your options. So for example, Ellie can only be working on the organization function if we want to maximize her output. Catherine can work on these 2. These are your options for Kath. For Joe, you have these 2. And for Bruce, you have this one option. So to make it easier, of course, we know that Ellie can only work on organizing. So let's cancel Ellie out. We already know that Ellie can only do organizing. And we know that in assignment problems, only one person can do one task. So with organization, we are going to assign this to Ellie. So these three can't take these anymore, and Ellie can't take any of these numbers anymore. Okay, so now let's look at Bruce, because Bruce has only 1 0, and it's for the leading function over here. So let's cross this out, because now Bruce will be the one to do this, because this is the only thing Bruce can do for the optimal output. And then here for Catherine can work on this and this, but Joseph can only work on this because he can't do organization anymore because Ellie's gonna be doing it. It's crossed out. That's why we give Joseph the control function over here. So let's cross this out. And finally, we see that Catherine gets the planning function. So let's take a look at this matrix. So we have Catherine for P, organization for Ellie, leading for Bruce, and controlling for Joseph. So let's go back here to this original matrix. So we know that Catherine gets planning. So this is the original matrix. Catherine gets planning. And then we have here Ellie gets organizing. So let's encircle this. And we have here leading goes to Bruce, who does it for 10. And we have here control, which we will give to Joseph. So now, if we do the objective function, we're going to see that only these values, so the objective function will ultimately just look like 8 plus 5 plus 10 plus 11. And it can be better explained if we see it. So this is the reason why this is our objective function. So you notice that since we didn't choose 10 for Ellie can't do the 10 hours of planning, so it's gonna be 0. So the values that are not encircled over here, their coefficients, the x value will be 0, so they'll be canceled out. You'll just be left with 5x1b over here, which is essentially just 5 times 1 because x is 1. So here you have 8 plus 5 plus 10 plus 11. So now we know that the lowest total number for here is 34. So again, our objective is to determine the optimal assignment of employees to minimize the total completion time. The lowest completion time we get is 34 if we follow this combination. So planning goes to Catherine, organizing to Ellie, leading to Bruce, controlling to Joseph. And we get 34. For a more specific answer, we can specify that the optimal matching goes like this. So the total completion time that we can get, the lowest value is 34. If we have Catherine working on the planning for 8 units of time, and then Ellie 5 units of time for organizing, Bruce 10 units of time for leading, and Joseph 11 units of time for control.